all of you are going to be good stewards to the community, and part of that will be depositing, I guess, I don't know if it's going to be the best structure, but a useful model, hopefully.
Very good structure, yeah.
And something that people don't realize, I think they have a misconception of what an archive should be and what a resource should be for the community. And there's always a balance between being a gatekeeper, a validator, or just a repository. And depending on where you're coming, you sort of project your own wishes on other places. I know there was a talk about data, and we might get into that when we go into the roundtable. There was a joke that we'll just throw everything in Empire, and then we have all our data worries solved. I don't know if that's the way forward, but we'll see how that discussion turns out when we have a roundtable. So today we have Justin Flatt, who's a biocurator at the RSCB, PDB, acronyms. So Justin, what do you feel is the most robust part of the Cryo-EM workflow?
Well, obviously it's one depth. So that's when you deposit structures, right? That system never messes up, and you'll love, every minute that you're able to sit there and work on submitting your structure. So
you just have to learn to love it.
Yeah, exactly.
Take it away, Justin.
All right, so thanks to the organizers, thanks to Ed for inviting me to participate in this workshop. So my name is Justin Flatt, and I'm a biocurator at RCSB PDB. I've been in this role since fall of 2020. My background is in Cryo-EM, and during my time I've processed something like 6,000 EM entries, and so today I'll speak with you about best practices for deposition and validation. And so we're going to cover a lot in this hour, so I think first it's good that we understand how the archiving systems and standards that we use today were developed. We'll then switch to how we can keep up with rapid growth in the field. And then finally, I will speak on the topic of validation. If you do have questions or if you want something clarified, just go ahead and speak up, and I'll help you. And so let's go ahead and start with the big picture. We'll think about the roles that we all play in developing the archiving systems and standards that support them. And so if you've ever heard a talk from a member of RCSB, then chances are you've seen this slide. So the Protein Data Bank was started in 1971. And it began small, with just 7 X-ray crystal structures. 4 of them you can see on the slide here. Now, over time, growth has been dramatic. So today we're at over 250,000 structures, and these cover a vast array of molecular components and complexes across many biological systems. Now, this is only possible thanks to the generosity of more than 60,000 structural biologists around the world, as well as the coordinated efforts of the worldwide PDB that was established in 2003. And of course, Cryo-EM as we know it today, as you're learning this week, it wasn't part of the story back then. It was around that time that they were doing these pioneering experiments to show that you could freeze and image biological specimens using an electron microscope without causing significant damage or distortion to their structures. And those early breakthroughs opened the door for the field, and it paved the way for what's now been over 5 decades of continuous developments and improvements. And importantly, because of this, Cryo-EM has been completely transformed. So now it's no longer a niche technique. It's commonly used in labs around the world. And so I've been showing this slide for a couple of years now to predict when Cryo-EM would overtake X-ray crystallography. And so we knew that it was only a matter of time. Here we are in 2026, and it's happened. So this year, the number of EM-derived coordinate depositions that we receive is more than what we get from X-ray. And that trend is not going to be reversed. In fact, I think it's likely going to be that the gap only widens between these two methods in the years to come. And I won't go into too much detail here, as I know that we all have the background story, but a lot of this is due to the community's embrace of advanced technologies and standardized workflows. One of the things that I do want to point out is the critical importance of fair and sustainable data management. Fair meaning that data is findable, accessible, interoperable, and reusable. And in many ways, the progress, especially during the resolution revolution, is directly a result of this synergy between the EM community and members of the worldwide PDB. So you have the community focusing on advancing technology, using it responsibly. And then the worldwide PDB is really, hung up on this point about fair and sustainable data management. So thinking about data, making sure it's properly archived, curated, and shared broadly with the community. And it's that intimate connection, those interactions, that's really spurred all this growth. And there's no signs that progress is slowing down. So you can see that both EM maps and models continue to grow steadily in the public archives. And this is because we've spent so much time and effort developing trusted data repositories that operate on shared standards. And so I can highlight some of the key milestones here. So EMDB was established in 2002 as the global archive for EM maps. In 2006, the EM Data Resource Project was initiated to make sure that the standards and validation would be developed internationally. In 2012, Empire was put in place to acquire all image data. And then the last thing I'll point out is since 2016, all EM maps and models that are deposited, they pass through one dep, so they go through this unified deposition pipeline that's in place for X-ray and NMR, but they use the requirements that were set in place by the EM Data Resource Project. And so this has been a massive undertaking. We've had to organize many workshops and challenges to collect expert feedback, but the payoff has been incredible. So you can see we've had enormous growth since 2013, but if you consider the number of biocurators working at the worldwide PDB, so this is the global team. So in 2013, there were 20, and today there are slightly less, so there's only 17 of us. So, on the one hand, this speaks about the efficiency in the system, but at the same time, it highlights one of the ongoing challenges we have, which is flat funding and fixed resources. And this is something that doesn't only impact us, but it impacts you, the community, because we're moving more towards an era of larger, faster, more complex cryo-EM data depositions. Now, the key moving forward, it's been the driving force all along. It's you, it's the community. We're thankful to the EM people for their participation and support. We do recommend as well, or we have recognized as well the crystallographers, especially software developers that have been jumping the barrier to help improve the quality of high-resolution cryo-EM structures. And looking ahead, we expect to see more and more from data science and machine learning experts as we are in this new time where we see a lot going on with AI and automation. And already we see with projects like Cryo-ET Data Portal, some of these interesting things where, they give standardized, validated Cryo-ET data sets for training and benchmarking purposes. So what does this mean for you today, sitting here thinking about yourself as a depositor? Well, you are a critical part of the solution by adhering to community standards, by making sure that, you deposit complete and accurate data. And you may not feel like it right now, but likely in the future you can and will be an expert in cryo-EM. And then we rely on your feedback to make sure that these archives are delivering the highest quality data possible. And then as the standards are, rolling out, it's our job to make sure that they're implemented and to make sure data is freely and globally accessible. And so to do this, we have a consortium where we have geographically distributed partner sites that each contribute regional resources so that we can meet the needs of the global community. And so current members are RCSB, PDB, there's PDBE, PDBJ, PDBC, there's specialist repositories BMRB and EMDB. It's a mouthful. The key is that we're all working together under expert guidance so that we can evolve the systems and standards as the science advances. Now, each site will offer its own unique views of the structure data, but when it comes to deposition, annotation, and validation, we're all working very closely together through one dep so that when structures are released, you'll know that they're reliable, comparable, reusable, regardless of your location. And we share responsibilities, but some of these roles are designated. So RCSB is the designated archive keeper for the PDB, and EMDB fulfills that role for the EMDB archive. So this is, often very challenging work, but it can be very exciting to see cryo-EM continue to push the boundaries in structural biology. And so, the PDB is helping us move beyond these single domain crystal structures to very massive, dynamic complexes. And because crystallization is not required, you have the molecular motion preserved in the vitreous ice, that gives access then to the full range conformational states. And so we're seeing more and more that researchers are very quick to adopt these new robust processing strategies. It's easier than ever now to download high quality computed structures. You can fit that to experimental density. Then you could refine it using a combination of machine learning, classical approaches. This is kind of moving us more towards an automated model building process. And then you have programs like CryoDragon that go a step further. You can do heterogeneous reconstructions and really explore the full spectrum of discrete structural states, sometimes at high resolution, depending on your workflow. And as these tools become more powerful, they become more accessible, this is giving us really an unprecedented opportunity to look at these very challenging complexes, ensembles, dynamics at a level of detail that was previously unimaginable. But we do have to be careful here. The community should continue to work closely with the worldwide PDB so that when users come to this data, they can really trust that what they're seeing reflects a biological reality. It's not just computational artifact. Now, with the increase in complexity, it also becomes more difficult to deposit data. So I have here, just as an example, a cryo-EM structure that requires multiple individual map depositions to be accepted to the archive. So we call this a composite structure. We've already been hearing about it this morning. And so, often what happens if you're not familiar with this strategy is that if you have a large structure and you're trying to analyze the whole thing at once, you'll have a map that has uneven quality. So rigid parts will show up very sharp. You can have then other areas that are poorly resolved due to flexibility or heterogeneity. And so what's become a common workaround is to take and split the map up into smaller parts. These are typically domains. You perform these focused refinements to produce then clear, high resolution maps of the components. The components are then combined. This is what we are referring to as the composite map. And hopefully what you see then is you have a more complete and accurate description of the full structure. Now, one of the issues here is that the conventional validation techniques, in particular Fourier shell correlation, don't apply to composite maps. And so for this reason, we have the policy that you do have to create all these supporting depositions. And this is really about making sure the data is properly validated. And you'll see, yes? A minimum resolution for the composite strategy. We don't set limits on resolution for maps. Yeah. Does that answer the question? Yeah. So you'll hear me talk quite a bit today about, yes?
So you have one structure, you split into different focus requirements, and then you have the ID for each of them.
Yeah, so what you do, so really it's for us, especially the PDB, we're really focused on the composite model, but yeah, the idea here is then that you'll have a composite map. That map up here, and I tried to color code things, but it's built using all of these individual components that were, you do the processing in isolation. And then this here's the consensus volume, but they all are submitted as their own map-only depositions. This is all a part of the same. So the consensus volume is the map prior to splitting it up into the components. And so that volume, it'll get its own deposition. It's a standard single particle and with half maps. And then you segment up into your focused regions, and each of these then is a single particle deposition that will have half maps as well. So it can get very involved, and I'll say more about this in a little while. But we do know that, again, this is a pain, and we need to do a much better job of streamlining how the deposition process works. All right, and so that was kind of it for an introduction. If there aren't any pressing questions or comments, I'll go ahead and switch to the next topic, which is looking at the challenges that lie ahead. And so with the rapid growth in structures, the PDB expects to run out of 4-character IDs by 2028. And so to address this, we've introduced a new 12-character format. So it begins with a PDB underscore prefix followed by 8 characters. So by doing this, we'll have more than enough codes that we can assign in the future, and it makes it easier to identify entries in the literature. The catch, though, and this is difficult for some, is that the extended IDs are not supported by the legacy PDB file format. And so that means no more new PDB files in the future. Everyone needs to move on, and the sooner the better, to ensure compatibility across tools, workflows, and for automated text mining. And so to help with this, we put together a dedicated web page that has project details, documentation, FAQs, and helpful tools. You can access it using the QR code or the URL on the slide. And so in the public files, they all contain these extended IDs. You can find them in the database to categories. So for example, here you have legacy ID 4HHB, which now also appears in its extended form. And so this ensures compatibility. We put files on GitHub to support testing and integration efforts. And so we recommend everyone to start using these resources now to plan for what's to come. Also, data APIs will support extended IDs by 2027, which is at least a full year before rollout of the next generation archive. And so the transition's well underway. The format of the future is PDBX and MMSIF. So why is that a good thing? Well, first, we don't really have a choice. The legacy PDB file format was rigid, so it has these fixed column positions, meaning that when you deposit a model, it's capped at 62 chains and less than 100,000 atoms. So that makes it impossible to represent many of today's large cryo-EM structures. And even small molecules will break the format now when they're defined using these new 5-character CCD IDs. So that's one reason we have to move on. The second reason is it will make our lives easier. The fixed, the legacy PDB format relied on fixed template records for remarks. It's been frozen since 2012 because it's simply not extensible. And while many people do like the simple layout, you have to keep in mind that it is difficult to extract metadata. It's often error prone if you're using automated tools. Now, in contrast, PDBX MMSIF removes all of these barriers, so it will support data values of any width. It organizes the information into structured categories, and it's extensible, meaning we can change it. So we can make adjustments for new methods, new technology, so that data is accurate and useful to the community as things develop. Also, it's human and machine readable, meaning that it's easy to integrate into modern workflows. And so this isn't just there to replace the PDB file, it's designed to be future-proof so that it can grow to meet the needs of the community. And so how do you read a PDBX MMSIF file? What's it look like on the inside? So the core of the format is surrounded around these data items. They follow very simple structures. So you see here you have a category name and an attribute name separated by a period. So I'm showing this is the EM sample support category. Notice how each line begins with an underscore, and each line is a data item that contains a single piece of metadata. And so when you have a data item storing just one value, we call that the key style, the key value style. If you have a data item that stores multiple related values, it switches to the tabular style. And you'll see at the beginning of the categories, the loop underscore keyword. And so both these styles are in the file. And it's a simple design that makes it human readable, and it allows us to accommodate, all types of complex metadata. Now, all of the, most popular refinement programs, visualization tools already support PDBX and MMSIF, so you don't have to wait to transition. You can do it now. You won't lose any functionality or compatibility. And to help, we've put together this user guide. It has examples, clear explanations, so you can see exactly what data looks like in practice. And so whether you're building a structure, refining a model, or just looking at a complicated assembly, this is the file type that you'll want to use. And while this may be a bit involved for some to make the adjustment, it really is worth it, as PDBX MMSIF really does enable deeper insights and broader impact for your cryo-EM data. And so the format covers the entire EM workflow from sample prep, vitrification, imaging, image processing, down to modeling and validation. So each of these steps is backed by a dedicated set of terms in the EM extension dictionary, and we're constantly reviewing and updating it. Also, as you have new methods or technologies emerge, we can expand the dictionary to capture them. In this way, this data will be useful. And so hopefully, this makes you kind of accepting and feel good about using the format, and you're wondering how to make the most of your structure in PDBX MMSIF, which, by the way, you'll hear it sometimes referred to as MMSIF as well. I may do it in the talk here. But this is where OneDep comes into play and can remove the guesswork from the process. And so OneDep is the unified deposition system that we've designed to accept submissions from the major experimental techniques, so EM, X-ray, and NMR through this single integrated workflow. And so for you, it's nice because it will ensure high quality submissions, it captures essential metadata, it performs quality checks, and it prevents incomplete submissions. And then on our end, it simplifies annotation. We use it to manage version control, and it streamlines data exchange among the worldwide PDB data centers. And just like the data standards themselves, it does continue to prove in time so that it's useful to the community. And so efficiency is a high priority in the design. And so far, the tool has kept pace with the growing number of depositions we see each year. So this is what breakdown looks like so far in 2026. And speed is not just about the tool and its design, but it's how you use it. So when you upload a structure, hopefully it's in the MMSIF format, OneDep will then take and pull all available information, and it takes you step by step through any missing metadata. And so mandatory items are highlighted in red. If you provide values that are outside of expected ranges, the system will let you know. And if you need help, you just send the message through the session, and we'll be very quick to jump in and try to make sure that you're not wasting precious time. And so I have some tips here to keep your depositions running smoothly. So first, please do take advantage of our training opportunities. We regularly offer these webinars and office hours. This would be a low commitment for you, and it can save you time and prevent confusion. Always prepare before you deposit. So a typical EM entry will have several maps, a mask, an FSC curve, often a model. We have tools like PDB extract, which I'll talk about in a little while, and the validation server that allow you to check and organize your files in advance so that later on, hopefully you don't have to unlock an entry and make corrections. Also remember you're not doing this alone. So when you submit an entry, it's going to be assigned to a biocurator, and it's this person's job to help make your entries useful to the community as possible. And so you can always reach out for help. The preferred way is through the session because it's properly archived, but you can also send a message to deposit help. And sometimes we reach out. So if you ever get something from us, please don't ignore it. We really try not to bother you. It means that we really need your help. And likewise, do not ignore the process results or the correspondence we send. Do what you can to fix mistakes. And in general, really do put time in, strive to be as complete and accurate as possible when you're describing all aspects of your structure, from the EM workflow to sequences to ligand descriptions. All of this stuff matters. And it does take time. So, you may be thinking, this is going to take up a lot of my afternoon and I just need the code so I can submit my paper. But really, you do want to put in the time. It's going to help people when they want to use your data later. And that's what it's really about, is maximizing the impact. You don't want to release this to the archive and then have it sit there and not be noticed. Question? Yes?
Yeah, for the capturing of workflow stuff, whenever I've done this in the past, it seems like a lot of those items have not been updated in a very long time, and they don't really, they require everything to be entered manually, even though a lot of that information could be captured from the software you're using.
Yeah.
So is that something that
we're actively working on it? So are you talking about in terms of being outdated, the DEP UI, just like the behavior, or even are you talking about the dictionary itself?
What's written there, right? In terms of reconstruction method and so on.
Yeah.
Some of those options are not really relevant anymore, and a lot of them could be automatically captured.
Yeah. So we do have
a lot of the metadata that people are entering now you wouldn't rely on.
Yeah. This is true. I mean, so we do have a 3-year project that's underway right now to improve one-dep, to streamline deposition, and this is, it does involve working directly with these major, software developers on trying to make it to where you have these files that are deposition ready, the metadata is in there, and it's a good point. I think we should go back and really think about, how things have moved and be very thoughtful with what data we capture and, just assess how things are used.
Like, for example, it'll ask you how many classes did you use, and like, often there's not necessarily an answer to that question for
Yeah.
a specific deposition. 'Cause
Yeah.
you might be depositing a local refinement or part of something.
Yeah.
You can't
It
answer
is,
that.
yeah. It's difficult, and probably we're seeing a bit of a fracture there and some, splintering even from the fact that it's really designed and optimized for single model representation
Yeah.
and like a very, kind of simplistic path forward, in how you produce a model. And so, yeah, I think like these composite entries are really banging at the door now, showing us that, we have to be more sophisticated and really make sure the data is, linked together and that, this information's something people would use and not just, a requirement that's put on people. So, yeah, this is a good point. And so, yes? You can, unless it's released. Or, so when you deposit, it is possible to withdraw entries. If a paper is published describing the structure, the policy is that we release the data. And we do that so that the community can access it and really judge for themselves and maybe diagnose, if some really strange things are going on. But yeah, before it's released, as long as there's not a paper, you can withdraw it. And then, it has been assigned a code. That code will always be in the database, but it will have withdrawn status next to it. So, yeah.
Another thought on that regard. Has the PDB thought at all about how to deal with preprints, or rather how to deal with...
Yeah, there is a policy around that. I don't know if it's consistently applied by everyone, but they treat preprints as publications. And so if there's a preprint there, I mean, they're not going to, a biocurator won't release a structure unless it's ID'd somewhere very clearly in the paper. So even if you can tell from the title,
It would be nice to have the equivalent of a preprint for PDB.
I see.
When we're submitting a structure for review, these
Yeah.
days, the structure and the maps go to reviewers. And certainly as a reviewer myself, I would try
You want
as
to
a structural
improve.
biologist to
Yeah.
improve things,
Yeah.
to identify errors, and hopefully the author will correct those errors.
Yeah.
If that requires withdrawing and redeposition of an existing
Well, it would be
structure,
obsoleted. It's not withdrawal.
right,
It
then I
is.
guess you get
yeah.
where I'm coming from.
Yeah.
It might be useful to have a designation for structures which are like a preprint marker.
Yeah.
Structures that are,
Yeah.
nearly there, but in progress, you know what I mean?
Yeah. So, I'll definitely take that back and we can talk about it
Might make people more willing to
Yeah.
make their structures available at the
early
preprint
on.
stage.
Yeah.
If they can say, okay, this is a preprint structure,
Mhm.
caveat of that,
Yeah.
and it will be updated to the final version of record when the paper is
Yeah.
published.
And one thing too about kind of this, what you're describing that I think is relevant is that you can version coordinates. So it is always possible to, even after structure's released, you can upload revised coordinates if you have corrections to make. You keep the same PDB ID and then we have an audit history so you can see what was changed. But the MDB policy is that, the primary map cannot be updated. So if the problem is with the reconstruction, you have to, create a new deposition, supersede the old.
Also, you
yeah.
probably don't want to be doing any version updates after you've published the paper because you want to make sure that whatever people...
Yeah, this is the logic for the maps. Yeah, now the derived data, the coordinates, they allowed it. I mean, you can see, for example, during the pandemic, people were rushing to put these spike structures out. And, then we see later on, people are doing a lot of versioning. They have time to...
Access the older versions.
You can.
You can?
Yeah, it's not what we're showing to you when you're at rcsb.org, but yeah, you can, FTP, you can, so I could send instructions about, going in and,
Or access them from the website.
no, not directly from, the public websites, yes?
But the preprint structure, we should be able to, that's accessible to the reviewers, right? I assume the...
Well, usually when you'll supply your coordinates and maps for the reviewers.
We stay,
Directly, not out, you couldn't access to the PDB.
yeah, we don't, we operate under strict confidentiality. So we recommend people do this kind of thing, sharing the,
So in that case, we don't have to upstream, but we can just modify, if there's a recommendation review, we could modify the structure and then deposit, right? Continue.
yeah, you could think about when you deposit. That's another thing. It's, timing is really important, I think, because, and even when you think about how long it can take to publish, the policy is that we hold it for a year. And then we look to see if it was published or, there's possibilities to withdrawal. Sometimes we'll extend the hold for peer review, but yeah, I think timing is a very important factor in
Well,
this.
after we publish, right, and then there's something wrong, right? So we have obsolete the structure, right? But then can then we open it and, access to the obsolete,
It is accessible, but not at our public website. So we keep in the, archive all of this, as part of the record if it was released.
When they look at the one that superseded, PDB, right, the one that superseded.
Well, yeah, when we put in the supersede record, then if they go to RCSB and let's say they're looking at the paper and they type the code in the paper, it will automatically redirect them to the improved structure. But
For the two versions, the old one.
yeah, but the old one won't, it's not even available to users. So no, it's through FTP, like it's a different process to do that. But then, yeah, I mean, some people are trying to go back and look at these older versions, but yeah, that's not something that's,
It might be useful to have that accessible just so that, if you're looking at a paper and the structure has then been updated, it would be good to know, okay, this was what they were talking about, right? Even in the same
Yeah.
way as you can always view a retracted paper, right? You can
Right.
still access the
Yeah.
paper and see what's being said. It hasn't
Yeah.
disappeared from existence.
yeah,
So having it as a way to say, okay, how has this changed? So that you can look back at whatever version was associated with the paper of record. That might be useful.
yeah, I think even for the educational
It
purposes
also
and
might-
best
it might
practices.
encourage people to be more, proactive about improving structures that have already deposited.
Yeah,
If they know that it's not making things like inconsistent with what they've
yeah.
published, right?
Yeah, I get it. Yeah. Okay. So, yeah, these are just tips, do put in the time. Let's, maximize the data. Now, when you sign on to OneDep, we do recommend that you use ORCID, as this will give you easy access to all of your entries. You don't have to worry about passwords, but do keep in mind that not all features have been fully implemented yet, and so this should get better in time. When you start a deposition, please be careful when you choose the entry type, because this sets the requirements and it determines whether you're issued a PDB ID, an EMD ID, or both. And if you complete this page, once you complete it, there's no going back. And so you really do need to choose carefully. Now, when you made the choice, this is when OneDep will come in and set the minimal file upload requirements to prevent an incomplete submission. And so if your entry includes a model, you can upload the coordinates either as a PDB file or MMSIF. An EM entry will always have a primary map associated with it. If you're depositing an EM model only entry, you must link it to a previously deposited map. All EM entries require a public image. Only some EM entries require half maps. So this is single particle, subtomogram averaging, and helical because it's used during validation. And then you have options to upload various types of other files. So for example, you can upload your FSC curve, the mask that you used when you were estimating resolution, as well as any additional half maps. Helpful additional maps, sorry. And I recommend too here, outside of OneDep, be sure to deposit to Empire is the best practice for preserving and sharing your raw data.
So,
Yes?
two things. Regarding Empire, so right now I think you can only do that after you already have an EMDB entry. Is that right, or am I confused there?
I don't think that, are you talking about depositing to Empire?
Yeah, exactly. You can't initialize Empire until you've got your EMDB. Is that right?
I have not done this in several years, but I think it's uncoupled. One issue that we see is people come back and they want to link their data to an Empire deposition. So I know they're doing it, and we're processing. They're interested. I mean, they've submitted it at this point, but and sometimes they'll ask us to do it, and then they're like, well, it doesn't have a DOI. We don't know this yet, but it actually is there if you look at the structure, but yeah.
The other thing is the additional maps. So the additional maps, when you go to EMDB, it'll just say like additional map 1, additional map 2, which is not terribly helpful.
Yeah, it's not.
It would be useful if there was a way to.
So there is actually, and that's, I'll go ahead and switch to the next slide, and I'll work that in, but this is the file upload menu. It really is the first critical step that you take in making your entry useful to the community. So upload, all helpful files, including additional maps, and be sure to give clear description. So if you put a description for an additional map, in the box, that will appear on EMDB. So what happens sometimes is that, we have depositors, like we've had cases where someone will upload 100 additional maps and give no details. And that's like a graveyard. I mean, nobody,
knows what they are.
Exactly, yeah. I mean, I guess if they put in the paper or the supplemental, but
yeah. Has additional maps, they'll just be labeled additional map 1 and additional map 2.
Yeah, it has such a generic kind of format. And usually,
I think part of the issue is every time you reload this page, if you had to load it a couple of times, it wipes whatever you typed in.
Well, the DepUI though it is not reflecting the most up-to-date annotation, what's in the model file. So it is buggy, and this is something that we are trying to improve. So you have to be careful, looking at the DepUI and like trying to make sense after we send the process files, because there are times it would just stop updating things, but if it does come through, it should. I mean, I always check this at least. I mean, I sometimes we do have instances where the EM map category just kind of goes crazy, but.
I wonder if it'd be useful to have some kind of preview for depositors. So like after you've deposited everything, this is what it's going to look like to an external user, because people might not realize that, when an external user goes.
That could be interesting, like even a video on one of our data outlets. Yeah.
Some kind of private link, I don't know, but like something where you can see
Yeah,
this is how it's going to the public.
Yeah, I
Because
think.
people might not realize, let's say a postdoc in the lab has been doing the depositing and whatever, they haven't filled in that thing, some kind of final check to say, this is what it's going to look like to everybody, are you okay with this?
Yeah, I see what you're saying, yeah.
Because it's
Yeah, I'll
a very
take that.
complicated
Yeah,
process, it's
yeah,
easy to miss
sure.
things, and it would be good to be able to check, okay, no, I really want to have EM workflow information in there, and we missed that. Oh, no, I really want to make sure these additional maps are clearly labeled so that people can tell what they are and what to use.
Yeah, seems like a reasonable place to try and attack that is kind of reworking validation results, like having an executive summary, maybe a checker in there that shows things that are missing, things are, like a summary of. Yeah, it's kind of, for some reason I'm thinking as you say this, how they have the image in a paper where you see like the workflow and you can kind of follow what's been done and see where there's missing. Yeah, that's a very good idea. And so, please give details. While on the topic of file uploads and data sharing, I do want to talk about a growing challenge that we're seeing with EM depositions, which is batch submission. So this is where you have a single study and you have a set of related structures. This is something that is extremely common. We already heard about it in the first talk this morning, in a way, how these, sometimes you're working with many maps. You have issues sometimes with modeling. I'll discuss this, here in these slides. But I think that composite structures actually is a very nice way to introduce this issue. And so, these have become popular because when you do local refinement on smaller areas of the map, it typically improves local quality, and this makes model building easier, but at the same time, it makes depositing data much harder, and that's because of the EMDB policy. And so if you use this strategy, you will have to create a deposition for the consensus volume. So this is what it looks like. Global refinement, you haven't split it up, done targeted refinement, so it gets its own deposition. And then you have to do the same for any locally refined maps. And then those are deposited alongside your composite map deposition. The composite map has to be clearly labeled, has to be linked to these source maps, and paired with the coordinates for proper validation. Now, we didn't make these rules. This comes from experts in the community. But if you mess any part of this up, it can compromise the usefulness of your data. And just imagine what this can look like if you have multiple composite models. So just this week, I was processing a batch from someone in this local area that included over 50 depositions because they had several of these composite models. So this can end up being a lot of work when you're the depositor, and you have to pay very careful attention. And so we do have sort of a recommended workflow here. Before you do anything, please go and check out the EMDB composite map deposition guide so that you can fully understand the process. We think it's best that you start by creating depositions for the supporting maps. These can be map only, labeled as single particle, and you must upload half maps. And it's only after you've created these depositions and submitted them that you then go and make the deposition for the composite map. This will look unlike any of the other entries, in that you answer yes to this question of, is this a composite map deposition? This will be the only entry that has the coordinates for the full structure, and we do not require half maps, though we do have cases where depositors sometimes will upload composite half maps, and we don't fuss about it. We'll accept that. And so, again, this is a bunch of work. In the end, to finalize the set, you have to make sure everything is properly linked together in this related category. And so, you can do this in one dep, or we can assist you with this while processing. And I understand probably for where you're at in this course, many of you, this is a lot of information right now, rules and guides. But I do think we should cover it, because I imagine if you're, processing and you end up depositing, there's a high chance that you're going to have structures that, you need to have this in mind how to do it. Now, another type of batch deposition that's not as common yet is when you have multiple models that are refined against the same map. And I'm not going to speak a lot about it, other than to say that we really don't want to see that you deposit the same map multiple times. Take and deposit the map once with one of the models, and then for all the other additional EM models, have them deposited as EM model only entries and link then to that map. If you have questions, you can ask, and this is an area where you need to watch, because the best practices are still evolving, and I do think there probably are going to be some significant changes to how we handle at least certain aspects of this in the future. Question?
With regards to the composite map thing,
Yeah.
so right now, how it's handled in terms of displaying the connections between those is they're just put in a single list under a layer of EM entries, where it will give
Right,
all
yes.
things that are part of the same thing, and also other ones that are related, right?
Let's see. Yeah, this is what it.
On the EMDB, if you go to
I don't know what it's doing here, but yeah, you can see this is what it at least looks like in the CIF file. Yeah, and then this is, God, sorry. And then, this is the dep UI, where you can go through.
On the EMDB page that
Yeah.
the way it's
Yeah.
disclosed is you go to the links, you have to go to the links thing, and then you go to the links thing, and under related EM volumes, you can see the other members of that composite map. But it doesn't give any, but it's just put in a single list, mushed together with any other related volumes, including like different classes and so on. There's no distinction between what the kind of relationship is, right? It's not broken out as, okay, this is a composite map, here's the consensus volume, these are the components of that consensus volume. Because often in workflows these days, we might have multiple different classes, each of which is a composite map.
Right.
And so when you have a complicated situation, that list becomes a mess. You can't tell it.
Right.
It would be useful to have something that was more relationally focused, where you could see, okay, there are these different classes that are part of the same experiment from the same sample, right? So you've got a hierarchy where you've got your data set, you've got your 3D classes, and then you've got your sub-particles, your sub-volumes, effectively, from a composite map. It would be useful if there was some way to display that in a manner where people can actually see what's going on, because it can be hard to correlate between what's on the EMDB and what's in the paper. Because in the paper, you'll have a workflow, but usually what you'll have is just some uninterpretable list of 50 different PDB and EMDB ideas at the end of the paper, but no way to easily tell what's what. It would be great if there was a way to deal with that on the EMDB side, so it was more easier to comprehend for these complicated cases.
Yeah, and it's interesting if you go back. So we started seeing these trickle in 2022, and now we have many of these cases. But if you go to the early ones, about the time that we were really getting the policy in place and enforcing it, you have cases too where people just taken one deposition and put everything there.
Yeah, all the additional.
And then the point you're making really hits home, because you may have multiple masks, multiple half maps, multiple, and depending on how precisely those links are, there, it can be a lot of work to figure out.
It's something
what
like
you're-
that summary slide you showed, which has the projections of each of those related maps.
Yeah, so even if
That's
it's,
already helpful, because you can look at that and say, oh, right, so that's,
Yeah.
that's that one, that's that
yeah, I
one.
feel like we should have it even
Something that's more graphical.
baked into the interface. Yeah, where like we have Molestar, but imagine you just, turn everything
Imagine
on
you
and then
just see-
it all appears and link different, show, yeah, it's a good point. So let's see. So yeah, the thing about batch depositions, the hard part is not really understanding how to deposit them. It's having to upload so many files, and then you have to type common metadata across all of these submissions. It's time consuming and tedious. And I'll just point out, as I mentioned a bit earlier, we do have a big project underway. So hopefully in the next couple of years, OneDep's improved, and we can have tools developed where we really streamline this process. I do want to advertise PDB extract. I don't know if people are using that right now, but this is offering some relief. And so what's nice about PDB extract is you can prepare your metadata, the common metadata, once during preparation, and then you reuse it across your whole batch of related entries. And it does go farther than what OneDep currently offers, by letting you upload all the common metadata instead of copying over just a limited subset from a previous deposition. And so if you'll get in the habit of using it, it can cut down on the repetitive work, it can minimize errors, and it just makes the deposition process more efficient. Now, the tool's recently been updated, and so now we have, it's easier to fetch custom metadata in a variety of ways. You can even now use an existing PDB ID or EM ID and then select exactly what metadata you want from that. The tool's easy to use. It's mostly just filling out this EM template that you reuse. And so if you're interested in testing out the improved tool, then just go search it online, click on the link, but make sure you include dev, at least for now. And that way you can access, the new features. Eventually it'll be in production. We just haven't got there yet. But yeah, once you have this populated, you can use it right away for, map-only depositions, or you can prepare coordinates. And I will point out that if you have very large batches, like, the one that I mentioned processing this week, we do have a command line version. You can integrate that into your pipeline, and you get really fast at working with the metadata for structures. And so if you're interested in that, please, reach out if you have questions or want to, need help setting that up. And this is just, very simple. We don't spend time, but it's showing how these files prepared by PDB extract are uploaded to OneDep. This is the simplest type of composite set that we get. So you have only one locally refined map, the consensus volume. But even in this case, this tool does speed up the process because it saves you from having to manually enter metadata. And so, again, just please, do try it, and, you can contact us and we will help if there's problems. So I've thrown a lot at you in terms of how to handle depositions in OneDep. But as we wrap up, this section, I think there's at least a couple of key takeaways that I hope really stick. So we work together to make accurate records. We share responsibility to make sure entries are complete. Please do let us know if you're working in OneDep and you notice that something is outdated or missing. And this way we can go and update the tool so that the records remain accurate. So as an example here, the Chameleon vitrification system was introduced by SPT LabTech in 2019, but it wasn't available in the OneDep pull-down menu for the instrument list until 2024. And so that meant for years, users couldn't select it from the pull-down menu. And so we add the device, and I immediately start seeing that it's showing up in entries. And so I got curious and went back and started looking through older depositions. And what I could see happening was that we had several depositors that would select spotted on, and then they would clarify elsewhere that they'd use the Chameleon. And while, spotted on is academic prototype, the Chameleon is much more advanced, commercially supported. And so now we're going back and trying to find and fix all of these records because, these inconsistencies can really confuse and slow down researchers that rely on, accurate metadata. And so, we share responsibility to keep up in the field. Please do tell us, we'll listen. we'll adjust and we can improve so that the record really remains accurate. The other thing here that I'll end with is that, all this time and effort that you put into your structure and its deposition really does improve everything for the field. This is why the center is so great, and this training that you get this week is so meaningful, and so please pay attention down to the smallest details. This is just a record that I shared to inspire you. So you can see here this depositor, when they described their starting model, made it very clear they're working with an experimental structure from the PDB. They also show that they're with its silico model from AlphaFold. They took time to, specify types, sources, accession codes. This makes it easy to, assess the reliability of a structure, or it makes it easier, and also to think about its novelty. They did the same thing for their pipeline. They even gave version numbers, and this is good for making meaningful comparisons across workflows. It helps to, adopt reproducible and robust protocols, and they did the same by making notes here for their model fitting and refinement. And just please, again, when you make depositions, try to go for these very detailed types of records. So this is the RCSB PDB team that we handle all of your EM depositions, and you can see we're up now to over 17,600, so quite a bit. So even if it's map only, if it's coming from the Americas, we're the ones to process it. I will point out that it's unfortunate we lost our long-term EM expert that was around before even OneDep existed. And at one point, I think it processed like a quarter of all entries in the EMDB. It's unexpected, but if you like this talk, if you would be interested in working with us, could put up with me, then, do consider applying, because we're going to try and plug this hole. We really need EM experts with how the archive trends are shaping up. We are the structure police, and so, I'll say that now as we talk about the topic of, validation. And so for the final part of the talk, I think, the key is to just remember that validation is not fixed. It's constantly evolving. The standards are continually being refined, and the worldwide PDB we rely on community input to guide what gets implemented in OneDep. And so we encourage everyone, stay up to date, follow the key publications, join in ongoing discussions. So what I'd like to do here is just share some insights. These are lessons learned from handling, 6,000 EM entries. And some of this will seem basic, but these are issues that I repeatedly encounter, in my work as a biocurator, and so I think they are worth considering. The first thing here is to never take an FSC at face value. So the field, commonly reports FSC using the 0.143 cutoff, but that number only describes the internal consistency between the half maps. We can't take it to mean that all regions are equally interpretable or that molecular features are actually resolved. Moreover, FSC curves can be artificially inflated. So for example, use a too tight mask, or if you have artifacts that are present across all the particles in your data, they can still strongly correlate. You end up with an estimate that's much higher than what you've truly captured in the map. And so to illustrate this, if you'll look at this reconstruction in the middle, so this map suffers from anisotropic resolution. It's due to preferred orientation. The depositor knew this. When they were depositing, they reported the resolution to be 12 angstroms. They ended up putting this map here is an additional map, and then for the primary, they went with a filtered version, as that was the level in the worst direction. So it's filtered to 12 angstroms, but notice how both CryoSpark and worldwide PDB validation calculated values that are much higher, so up to even 3.5. But when you look at this map, you don't see features consistent with that resolution, and it becomes obvious when you compare it to a different map from the same group. So this structure is analyzed as part of a larger complex. They performed a local reconstruction, got it to 3.2 angstroms, and the detail is clear. And so always, inspect your maps directly, and it can help to compare them to maps that are at a similar resolution if you want to really understand local map quality. So no substitute for the eye. Yes?
Is there any thought about providing either the possibility or the requirement to upload like 3D FSC or like directional FSCs? Because like NIC is a big
Yeah. It's probably it's the problem.
Don't necessarily pick it up. So,
I do not know of any immediate plans to do this, but I do think it's a great suggestion, and we can surely discuss it. I think it is worth bringing up. So you have a lot of good ideas today. So if you just make an email or something, or it's recorded, so I can go back with Notepad, and maybe you come and join the worldwide PDB in this new biocurator position. But yeah. So this is one insight. The second one I'll say here is to resist the temptation to make perfect-looking models from imperfect maps. So what you have here, this is the same structure deposited by different groups using different methods, so either subtomogram averaging or single particle EM. Now, if you were to look at the global metrics just for the model, you would think that this structure on the left is the better one. However, when you inspect the local density, the differences become striking. You can see that this model has been the outliers have been refined away within the broad density. Even these bulkier residues that you would expect to see, signal for at this resolution, you can see many of them are in completely different conformations than what you have in the 6HBC model. It's much better supported by experimental density. And so what we have here is an instance of a structure that has a very nice score, but it's wrong. And so we want to try and avoid this as much as possible. It can be challenging at times, but really, overfitting is something to always have in mind. And to help spot this issue, we did recently add the Q-score slider to the quality metrics. And this makes it easier to compare models fit against structures, at a similar resolution or against the whole archive. And, I'll have more to say about that in a couple of slides. But first, yeah.
What did the authors say with me?
Do what now?
The authors were interested in depositing information. What were they saying with you don't check for?
Are you, so sorry, I don't know if I heard you.
We assess the information that they deposited the same. Without they say, I'm just
Oh, yeah. Yeah, I mean, we in the correspondence, we were, bringing up certain issues. So if we see like density that just does not at all look like the resolution claim or various things, we do bring this kind of stuff up. We do not gatekeep at all. So we'll flag major issues, but ultimately it's a decision of the depositor. And to be honest, the responses we get can be a bit all over the place. I mean, some are really careful and they want to try and fix whatever they can. Some will fight back, and then others just don't even respond. And so, again, as soon as the paper goes out, like there's certain data I wouldn't release unless there's a publication, but once that paper's there, we get it out fast. Yes?
Something like Q-score for like the entire map or for like per region?
It's. I have a slide on it next, and if you have a question, if it doesn't make sense explanation, you can let me know. So, the point I was going to make next is that Q-scores are making it easier to detect exaggerated claims. And the way they work is they consider the local density around atoms. So if you have a sharp, well-defined peak, an atom will score high, close to 1. If the density gets weak, the score will drop towards 0. And then if you have an atom in empty space, it can even be a negative value. Before Q-scores, we were assessing fit to map using atom inclusion. And that's a very simple measure. It's basically looking at if an atom is inside density at the contour level recommended by the depositor. And so, it can be useful, especially for lower resolution structures, but it often makes models appear better supported than they really are. And so this is a case here. You can see the reported resolution is too good at 2.8. The depositor did give us a curve to support the claim. If you look by atom inclusion, it looks fine, but it's when you examine the Q-scores that it becomes immediately clear that this map lacks the level of detail that you would expect, for the reported resolution. And so it does, Q-scores are making it easier to spot these kind of too good scenarios. Yes?
That's a related question based on this, separate from my previous.
Yeah.
So if you have a map and you have a focus map, and it's not a composite, so you have the overall consensus map, and you just have a focus map of one region that you care about. If you're doing the deposition, the Q-score is going to be based on the main map, right?
It's based on the fitted structure inside the primary map,
Yes.
the main map that is deposited with.
Let's say, the authors of paper, whatever, like
Yeah.
the focus map is in the actual region of biological interest, and that
Yeah.
like has
Yeah.
better
Sure.
solvability. How can you, as the scientist,
Mhm.
sort of highlight that via the deposition?
It's a good question. So we this is why we recommend for like the consensus volume. So before you do the focus refinement, that it is a map-only entry, so you wouldn't even have the model there. For the focused refinements, if you really want to highlight a particular area because it's of a significant interest, then it's likely a good idea to include a model with that, and that's fine. If you do that, the only critical part of policy is just that whatever map model combination get deposited, the primary map should be the one that was used to build the model. And this is why I was saying earlier, like for the composite map, that's going to be the only one that gets the coordinates for like the full structure, because that one is the one that represents the full model. But for the focused refinements, it's perfectly acceptable if you want to deposit a model with that. It just needs to have that. Yeah, typically it's domains people are working with. I mean, sometimes it's more complicated, but yeah, you can, whatever density you used, to refine that local area against, you can just make that the pair and, deposit it, and then it gets, yes?
Like, how would you interpret a good versus a bad Q-score?
Okay. No matter what I do, I always would inspect maps visually, with the model inside. But I think, with the Q-score, you just have to remember that beyond 2.5 angstroms, as the density loses features, it becomes less meaningful. And by the time you get to 4 angstroms, it's not, you've lost enough atomic detail in your map, it's noisy enough that it's not very informative, I think. And so I think the range where you can really, be paying attention is anything below 3.7 to 4.
Like if you were in that range, like what would you say? Like for you, what would you say? Oh, this Q-score is borderline.
Well, it's resolution dependent. Yeah, I have a slide actually. I think I can get to that in a bit because when I emphasize ligands, but yeah, we'll get there. We'll get there very soon. Is there another question or yes?
And so this helps say how well the model fits to the map. I guess that Q-score.
Yes, yeah. So you fit the model, and then you're going and you make this ideal guess.
Similar to the RSCB score that on the one of the, is it similar to that one? RSCB score.
No, there's some fundamental differences in how it's calculated, but with the Q-score, I mean, again, you fit the model, then you're doing a Gaussian, this ideal representation for what the density should look like on a per atom basis, and then you calculate that against the map and compare the densities this way. And then, when you go to the validation report is in a CIF file, so or MMCIF, so you can, look then in a variety of ways. But typically, when we discuss ligand Q-scores, or, you can have an average for a full structure, you can have an average for a residue, or you can get really down into the, looking at even the atoms in a side chain, each of them. So I think it's striving to kind of answer a similar question about how much it approximates the density, but yeah. Yes?
Is the Q-score impacted by deleting residues? If you don't have a region that has good density, you just end up not modeling that region at all.
Yeah, if you don't model, I mean, it just won't, it won't show up. So, yeah, you have to think about, this kind of stuff when you're depositing. And the thing to keep in mind, I think ultimately, is that you want to be as accurate as possible and as truthful and transparent as possible for the experimental data you have, and not, some just very ideal, pristine, and you have to think too that over time, probably the tools keep getting better. And anyways, it's coming for your structure. So, you cut corners now and, probably on data out in like 5 years, we see some really sophisticated way of looking. And it's like, oh, there's like all these entries out there where they kind of were taking a shortcut and, we finally can understand it. But so that's Q-scores. The Q-score slider will help to see when, models fit is typical, better, or worse than expected. They're at the top of validation reports. And by including them in the summary, you can see the best models the field has to offer. You can also see these common challenges like preferred orientation. I included this specific example because it was very nicely discussed in a paper recently, so I do recommend to take time. It's not a long read, but that paper is a very good one. So, you know, it's like what we saw earlier. If you inspect that map up close, you would see detail along the preferred view. But when you switch to the orthogonal direction, it's, you know, featureless and elongated density. And so for that reason, you can see with the Q-score slider here that, you know, it scores low compared to, you know, this is against the entire archive, and then it gets even worse when you look at structures at a similar resolution. And so the last thing I'll do here, I, you know, think I've managed to pack as much as I can into 1 hour, is to give some insights about ligands. I think that's one of the really cool areas of cryo-EM right now, and it turns out it's super hard to find an optimal pose that satisfies both fit to map and coordinate space validation. So to do this, I'll use some of my previous work. And so a project I had was looking at these novel class of compounds that can target, neutralize enteroviruses and rhinoviruses. And the way they work is they sit in this conserved, well-defined pocket on the surface of capsids and form stabilizing contacts. And it's these interactions that make them show up very nicely in cryo-EM maps. But despite having such nice density, they were still really hard to model. I spent, you know, countless hours staring into the druggable pocket. You know, I tried doing MD, you know, these cryo-EM guided simulations, all sorts of tricks to try and refine the pose, and I didn't end, you know, at a perfect solution. And I think it was mostly the elbow region that was giving me a lot of trouble. But I bring this up to say that, you know, these resolutions that we, you know, now can routinely achieve, you know, it still is very hard to put a ligand in its environment, in the full environment, and to model it accurately. And so you have to use careful validation. You want every bit of information you can find to help model how you guide the interaction. And you also have to then have realistic expectations for what your density can and cannot tell you. And the Q-scores actually do a pretty good job on flagging issues. So if we keep going with this personal example, before I started the capsid inhibitor project, the group that I was a part of, this was Sarah Butcher's lab in Helsinki, they had already published one map trying to understand how these inhibitors work. And so the original map you can see was at 4. The average Q-score for the full structure is 0.45, which is not all that bad. But notice how the ligand Q-score drops to 0.2. And so that should raise an alarm. I mean, if you look in the pocket, you can see the density is not as well defined, and the pose is not, you know, so well supported. So I decided to go back and reprocess this data. And so I went back from scratch because I knew, you know, these compounds form very stable contacts. And I also had a really nice outcome looking at a different inhibitor bound to a different virus. That was the data I showed on the previous slide. And when I did it, it paid off. So this map here is improved. It's at 2.8. You can see that the Q-score for this, you know, here increased to 0.62. So this is kind of getting into this question about values. And then you can see the ligand Q, this is the key here. It is now much closer to the average Q for the full structure. And, you know, it's this enhancement that allowed me to then model the ligand to where it was a match more to the experimental data. And so, you know, the thing to be aware of is that ligands do often appear less resolved in reconstructions, and, you know, their Q-scores will lag for this reason. And so you really do want to pay attention to the discrepancy because it is that local density that determines how good your model can be. Yes? We are only starting to explore that, and actually I have a slide on ligand Q-score distribution across resolution bins. We're kind of getting into it now, you know, doing these more systematic studies. You know, it's still a question I think hasn't all the way matured because, well, there's many factors. We have to think about what's in the archive currently and then representation within each of those bins, things like this. But there is some interesting trends. I keep putting you off, but if you give me, yeah. Oh, sorry.
So one on the left, 4-action structure.
Sure.
That's the Q structure was a 0.25. Would you then accept that, or is this everything so low you're like that?
This structure is 4, so I would put very minimal value into the Q-score period at this level. I mean, yeah. You can see, by the way, the slider shows up pretty well because, you know, we were always kind of conservative with, of course, like we heard, there's no single resolution. We're conservative in how we report. We did have features in there that kind of really, made it look more or less okay. I mean, it's definitely not like the newer one. But yes?
I mean, the density's pretty crummy on the left of the ligand in the first place. So,
Yeah.
we talked a little bit about judgment calls for modeling
Yeah.
ligands and what you don't really have that kind of feedback that crystallography has.
Yeah.
And, looking at the difference map after refinement.
Yeah.
And certainly you've got like some side chains on the right, some heteroatoms to kind of more correctly locate those interactions for your
Right.
ligand. You don't necessarily think that they've done an incorrect job on the left. They do the best.
Yeah, I think it's a good
Might end
point.
up with like
Yeah.
1.5 extra structure at some point for the right and find out that it's
Yeah.
not quite ideal. So just in terms of a trajectory of like the improvement of certain models as the maps improve in the archive, I guess the intention is not to flag models like this because they did the best they could.
Yeah, it's a good point. I think, and again, it's this where I was saying earlier, it's really important to just try to be as accurate as we can with the experimental, data we have, because, data's messy, and sometimes, it's okay when there's limitations and, they can see it when they look at the map and then they see in the reports.
Say blue line on the left. I mean, you don't have an new map to kind of.
You're talking about this way. This has these. So these two outcomes have different stereochemical geometries. So this ligand is it had to be. It kind of underwent a major correction when we had higher resolution. So we could say that as far as goodness of fit to data, it falls in the bottom quartile. I'm going to show this in a slide. I'm about to get into distribution. So you definitely would not, for that class in that resolution bin, say that this is, based on all the instances in the archive, that this is a very nice representation of what you can do with modeling at that level. So as has been said, you just see the density. It's like, whoa, this is, we have to be very careful with how we interpret it. I have a slide. It's coming up very quick. I did want to just quickly point out this paper. I thought it's really nice that Mark Herzig recently published, where he was showing that these deep learning density modifiers do have unpredictable effects, and in extreme cases, they can even completely remove ligands from maps. And this is something to be aware of because these tools are very common. Right now, we see lots of depositions. Yeah?
I have seen this in practice.
Yeah.
Completely deleted the ligands, and
Yeah.
it was kind of everyone was generating maps using these sorts of methods because they looked better.
Yeah.
But I think just to try and have as many maps as you can that are
Yeah.
But I guess as for the cryo community, why is it okay to posit maps that are kind of on the sort of tree?
Well, I feel as a representative, it wouldn't be my place to say beyond observing, waiting for like a consensus to form around this. I think it's still kind of early. I think what, again, we kind of simplify and reduce the kind of nuance in this question by just saying that we want the map that you use to refine, to build your model. And, I don't know if everybody's, it's hard to say. We, on good faith, say that someone has made the primary map the one they use for, refinement. But, we've kind of for now settled on that, kind of solution where it's like, okay, your primary map should be that one map. But I do think there is a bigger question tucked away in there. And especially as some of these tools are getting more and more trained on map model pairs in archives, and it's getting more into this AI and machine learning space. It's like, at what point is this experimental, or when does this turn into prediction? Is this,
Purely an experimental map at that point has undergone some treatment by AI.
I would just comment there that it's important to know what's going on behind the scenes. Not all of these tools are equivalent, they're not all doing the same thing, they're not all doing
Right.
Phoenix result, for example, that's not AI, it's just statistical density modification like we've done for years in crystallography. So it's not doing that, right? And even these different AI tools are doing different things, right? And so there's another tool which is mentioned there called AI Beacon,
Oh, yeah.
Beacon Chain, where it's actually doing some pretty sophisticated math to correct the effects of preferred orientation on your map, but it's not doing it using AI, it's not doing it deep learning, it cannot delete ligands. But the way these ones work, they can.
These
So you
nuances
just
are
need to
important.
know
Yeah.
what you're doing.
Yeah, and it's,
Yeah.
I guess if we're trying to be kind of, the positive spin is, there's some of them have things about them that are very attractive depending on the complex you're studying. And so I do think this image works on many levels. It used to be, I'm going to date myself here, but when I think back to how we were processing and modeling, you did the one tool approach. Like I was, can't rely on MDFF. Well, even going back to Freeline, which I don't know that people are using that now so much. But anyways, I think in the future, it's like we have to get more comfortable with really taking many tools and just very carefully comparing each one. And then it goes back to that point about we need then to think about how we deposit, probably get much more sophisticated, and then somehow make it to where people can kind of appreciate how each of these, views factor into that final.
The PDB is not looking to enforce particular.
Not right now. Again, the policy is just, the primary map needs to be the one that was used to build. And, again, you can see already there's a problem, because when you have a Frankenstein, yeah.
I think so long as you've provided your half maps, right?
Yeah.
So long as the raw
Right, okay.
data is there,
Yeah,
people
yeah.
can actually generate that reconstruction.
Yeah, and I think, earlier I had that example of anisotropic resolution, where the depositor gave us that, right? And I do think that there's no harm done in providing all this, making many depositions, letting them have their own EMD IDs where you can easily fetch them and describing them well. So like in their place, it was like they were doing this, I think, from going back and forth, I process that entry to, help understand like, the processing and like certain limitations, they describe it in the paper well, but they also were then like, well, if we compare both those structures, we can at least say this one part of this bigger structure doesn't undergo a conformational change, when it's in the larger complex. So it's like they were actually, still kind of hitting a biological question and then other things. So I do think probably, being more comprehensive in, or thinking about expanding the number of depositions, to really highlight these various maps, it's probably really important. So this is the one slide that I think may be helpful. I wanted to include, I think you'll find it interesting. This is doing kind of a bird's eye view of ligand quality. A few things I'll point out. The first thing is that if you go back just 10 years, cryo-EM was rarely used to describe ligands, but you can see that the number of depositions with ligands now has climbed rapidly, and we have many cases where you have oligosaccharides that are modeled. What's interesting as well is that we have the tool, the method being used now increasingly to describe ligands that the PDB has never seen. Now in the middle here, this is distribution of Q-score for ligands. This is a breakdown into different resolution bins. Sorry if the detail's hard to see, but if you go to the top, so this is the 1 to 2 angstrom bin, the median value, the black line is 0.66. And then as you work down through these bins, as the resolution worsens, it drops all the way at the bottom to 0.34. And so what that tells us is that a ligand's fit gets worse when the resolution decreases. Nothing, exciting in that. But I do think it's interesting to pay more attention to like the low end of the distribution. So when you look, for example, the lower 5th percentile, at the top it's 0.20. At the bottom it drops all the way to 0.10. So this would indicate we have a growing number of ligands that are unsupported by experimental density. And then you can also see that the spread widens as you go down, and you end up having long tails of poorly fitted ligands as your resolution gets worse. And to yes, sorry, I'm getting.
The manual fitting or what software you fit that, because you make comparison, but what kind of fitting is it?
I ask for this data from another annotator, so I can get back to you on that actually if you'll reach out to me specifically with the details for how this was generated, but I can't answer exactly how the.
Is there a way that easily distinguish there between cases where there just wasn't any density and people put in ligands into something that effectively wasn't there, and cases where there was actually pretty good ligand density but the authors just misfit it, right? Because both of those situations will give you a bad Q-score. But they're different in the sense that one of them can easily be resolved potentially in an automated fashion by remodeling the thing that's there, like a PDB redo kind of.
Yeah.
Whereas in the other case, it's just that there wasn't the ligand density was too poor to model, but people put a ligand in anyway.
Yeah.
Like something like how.
So would you say in the one scenario, this is like atoms even in empty space, like there's no trace of like the density there, or?
No trace, but like you just have some random noise density or something that's waters or whatever, and people would put a ligand into it. That definitely happens. I've seen that. But there are other cases where, so it's like the difference between, let's say you have a bad Q score for a residue because, let's say a phenylalanine was placed over here and the side chain density is over there, right? That's different from a bad Q score because there just wasn't a side chain density, right? Or the resolution was too poor, so you don't get any correlation between the atomic model and the
It's really hard to answer that question because right now the Q scores are mostly being calculated for the backbone. I haven't looked at as much until we very recently got into this, trying to look more into like atoms and side chains and analyzing.
which is quite useful. It's not used as much these days. But
So I hope this kind of thing will be out there for people to use because it is an issue, and especially if in your structure maybe that ligand, you have several ligands, it may not be one that is interesting to you in the story you tell, but you have to remember with any structure, it's like with the spike protein and the glycans, there's a whole field out there that wants to look at just that one thing. And sometimes, I think things are an afterthought, and then it's bad because people, will base future experiments on it. For this, to make it a little bit more concrete, I wanted to add, these are the ligands from the previous slide. So this is where I reprocessed the data, and you can see that the ligand Q score is very close to the median score. So 0.52, it's 0.53 for its resolution bin. And then this is the poorly fit ligand from the original map, and it's in the lower quartile, the bottom quartile. And so, together this shows Cryo-EM has a lot of potential. It is very useful for ligands, but it demands vigilance. You have to go and inspect every instance of a ligand, whether it's your own, data or you want to make use of someone else's structure. There's no way around it. So I will give some ideas about best practices for modeling and validation, and we're officially done. I'm sure you guys are kind of tired at this point. But the first thing I would say is to validate early and validate often. Use every tool out there that you can find, including the validation server from the Worldwide PDB, and do it throughout your process. So don't wait until like the very last minute when you think it's time to go and deposit. This point was raised earlier, but and it's hard to achieve, but do everything possible to work with the best quality map you can produce, and then model only to the level of detail that the resolution truly supports. It can be tempting to push limits, but restraint is key to accuracy. You don't want to overfit and go beyond and say more than what your data can actually do. Yes. You're talking about the various calculations in there. It's being worked on. I mean, we would now, the thing is, I was processing energy this week. We get things like these doublet microtubules, so like 160 chains, over 500,000 residues, and you're like, one dep's going to go on life support. Like, does this come through? Like, it's validation. Like, it can take a week even for these reports to run. They're kind of way too long, and it's stressful for both sides. So
comparing it to the Phoenix validation, like the built-in validation tool at Phoenix, and while that one is faster, sometimes the numbers themselves aren't fully in agreement. So I was wondering, is there going to be an effort to maybe standardize things across? I don't know who's right and who's wrong, but just I guess way to have it be consistent so that when I'm validating it in Phoenix, I know that it will be. What
would be great would be a locally run version of the validation tool, right? So that.
Yeah, well, we have the standalone validations. It at least,
still run in the cloud and it's still slow, right?
Well, you can I think install and run it. Yeah, locally.
I install locally. I would totally do that.
Yeah, but
fast feedback. Because it takes every time you're trying to
we have to improve this a lot. I mean, you had mentioned the differences, discrepancies, and the PDB will intentionally go a bit slower. So like the version of old property we use is not going to be probably what, Phoenix is out there, putting for users. So you have issues like that. But yeah, I mean, the validation report can be a pain. And especially, you think about the preliminary val report. So in one dep, you have 15 minutes, maybe max, to put in metadata for a batch, but then you're waiting for the prelim report. And if you're really careful with validation, chances are you've already done this on the validation server. So, yeah, we talked to people, I was talking to a group recently, and they're like, somehow it needs to be better streamlined.
So there is a local version of Validation Suite, but it was last updated in 2004.
Ah, is that true? Oh, that's embarrassing.
So
I'm not sure. I'm going to claim that's not true, but I'll get back to you on that. I can go back and raise some alarms. So prepare in advance. Also inspect every part of your structure down to the water molecules and ions, because this can reveal inconsistencies that our broader metrics could miss. Do try to fix things. We kind of touched on it earlier, but you will be able, if you make mistakes, or something slips by, you don't have to panic. You can upload revised coordinates after you've released a structure and keep the PDB ID. But if something is wrong with the map, you do have to create a deposition and then supersede, because of the MDB policy, the one that's already out there. And so I have this picture here that I wanted to include just to inspire you. This is coming from Watch Use Group with help from Greg Pintilli. And I like to go back and really stare at these types of structures, because the level of detail and what was achieved is like amazing. And so if you haven't done it, I do recommend to go and sort cryo-EM structures by resolution, by quality, and have a look, because I think it helps to train the eye, and it gives you kind of a new sense or skill at being able to think about what a map can support. And when you're at more challenging resolutions, that's like gets really key there. And the final thing is just make the most of the community. I mean, you're doing it this week here at the meeting. Continue to ask questions, make requests, highlight success, criticize everything. I mean, these conversations really improve the science, and it keeps everything moving forward. And I know we're way over time. This is just, our team, we're not automated all the way. So if you get a validation report from computers, we do have humans, I'm proof. And then, yeah, just please stay connected. We have, this upcoming webinar. We have other things. Everything's kept on PDB 101. So, you'd have plenty of chances to go back. And this particular one was very good that recently came out. But okay, that's kind of it.